for chapter 7. So should I like type out the question to the side since it's kind of one of those, it has a lot of, it's kind of long.
Yeah, sure. If you want to type the question, might be easier.
Okay, I'll do that. Okay.
Okay, just saw it pop up. Okay, so company makes 20,000 laptops each year. Oh, okay, so this is the gist of the question. Okay, so I guess I'll just read it in case anyone's watching. So a company makes 20,000 laptops each year. The company knows the laptops last an average of 38 months with a standard deviation of 6 months. The company offers a 36-month warranty. If the laptop life is normally distributed, the percentage of laptops that will stop working before the warranty expires is blank. So we'll just tackle that part first, and then I'll do the second part because the second part is very related. Okay, so here's the thing, I guess. So I always start with just like drawings of what we're talking about here. So here we want to know, or we know a few things. They tell us, okay, in the population, so the average lifespan. So here the question is we're just trying to figure out what's the lifespan of a laptop. That is generally the thing they're asking for. And so what they tell us are the two things we really need to solve it, which is we know that the average lifespan is 38 months, and they tell us that the standard deviation of the lifespan is 6 months. So this is basically sufficient to describe, and they tell us that they're normally distributed. So now we can say, well, we know this center here is 38, and this is it's at 44, right? It's 38 plus 6. So this is one standard deviation above. So this is just to give me an idea of like the shape of it. And what they want to know is this. If they have a warranty that guarantees things out to 36 months, the question is the percentage of laptops that will stop working before the warranty expires. So they want to know essentially what does all this proportion end up being. So this whole curve describes the lifespan of each laptop. This is just saying of all the laptops that they make, we know that on average they last 38 months before they break, and that the standard deviation of how long they last is 6 months. So we can put those two into here and draw kind of a picture of here's the expected lifespan. Like at random, each laptop, we'll have a few that don't last very long, a few that last very long. An overwhelming majority will fall somewhere in this range.
So is it like negative 0.25 as a z-score? Or what is it? Like
yeah, so that's what we're trying to do. We just want to know, okay, so I need to solve this problem, I just need to turn this thing into a z-score. I need to get that 36. So what's the z of 36 here? It's equal to, what's the formulation we're going to use? Like, how do we get z-scores for anything?
You have to like find, like, compared to the standard deviation.
All right, so yeah, so what is the actual form of that? I guess I'm trying to get you to generate it, because if I just tell you, it's not that helpful to you. Like, literally, so even without considering this problem, what is the z-score formula?
From like calculating it from what? Like from something from the Ross?
If assuming I have no numbers and you just want to tell me like, here's a formula and that we're going to plug things into it. So like if I just say z is equal to, what goes over here?
Isn't it like the average, like the number minus the average?
Yeah, so that's the x score is our number. We subtract out the average.
So that gives by the standard deviation?
Yeah.
Right.
So this is our distance and how far away are we from the average, and then we divide by the standard deviation to turn whatever this distance is into standard deviation units. So if we want the z of 36, we're just plugging in the stuff we know, right? It's the same as this. We just say 36 minus 38, divide that by 6. So we get negative 2 over 6. What's that? Negative third? Negative 0.33 forever, right? 2/6.
Okay.
Oh, no, that's 6. Oh, awesome. Mark of the beast. So negative 0.66, because we have, this is 2 over 6. Oh, it's actually negative 2. Yeah. I'm back the other direction.
I think you're right before.
Okay, this is why I also do all the math like this, because I will trick myself into trying to think I found shorthands. Yeah, so it's negative 0.333, repeating forever.
So then it's 30. It's like around 37%.
Yeah, so if you just look this up on the z table, that'll tell you how much is to the left, especially for the table we're using for the exam. It just directly gives you this answer, right? If you know this is equal to some z value, the table will just say, for that z value, this is how many are less than it.
Okay.
So this is the z.
So that's like that's the first part of the problem.
Yeah.
So that's transforming from a raw score to a z-score.
Yeah, because they want to know about individual laptops. Like if I sell you a laptop, what's the chance of that laptop needing warranty service, apparently, right? Because if it dies at 35 months and 11 months and 29 days, I still owe you a new laptop. So they want to know how many new laptops am I going to need to replace or fix. Okay. So the second part of the problem is now saying, suppose that the company has 200 salespeople who sell laptops, each sells 9. For each salesperson, you calculate the mean time before the laptop stops working. The percentage of salespeople below 36 months is... yeah, okay. So this is a weird formulation.
Do you do like the standard deviation divided by the square root of the population? You're trying to find the standard error of the mean, or is it something different?
It's actually exactly that. Like, so here, right, here's all we're doing. We're saying the regular z-score, if we're talking about scores, is this one. But the z-score, if we're talking about groups of scores, so right here we say we have n equals 9 because each salesperson is going to sell 9 laptops, and we're going to calculate their average, the average time they expire. Let me make sure that's the exact way they're wording it. Yeah. So, okay. So each is going to sell 9. So we want to know the average lifespan of the laptops each person sells.
So does that number 200 not matter?
Like, yeah, it ends up not mattering. So lots of times they'll throw red herrings at you like this just to see what numbers you're going to use. But really, if all we care about is we're saying we're going to take a group of 9 laptops. Somebody's going to sell them. But it doesn't really matter how many people are happening. We're just saying if we infinitely took groups of 9 people, where would we expect those 9 people groups or 9 laptop groups to average their lifespan?
So then would the standard error of the mean be 2?
Yeah. So this just the sigma, now we modify it to get standard error of the mean, which is sigma divided by square root 16, or square root of 9. I always use 16 because it easily reduces to 4. So this ends up being the square root of n. This ends up being what? Sigma is 6. That's 6 over 3. It's 2. And really, it's the exact same formula here. So we're just saying when we're talking about the sampling distribution, z is equal to x bar now is the average score we're interested in, right? Because now we're not interested in individual scores. But in this case, the average score they want to know about is the same thing. They want to know about 36. Okay. Right, so how many of the averages will be to the left of 36? What's different here is that this little thing we marked as 44 because the standard deviation was 6. Well, if we're talking about the sampling distribution, the standard deviation is now this, which is 2.
It's 2? Okay.
The standard error of the mean is, so that's 40. So you can see we basically just zoom in on this thing, like, right? It's the same shape. We're just zooming in closer to the middle because the scores are going to be less spread out. Okay. And now from here, we're just plugging in the same things because this is the x bar.
So it's 36
minus mu x bar.
Is it 36 minus 38 divided by?
Yeah. So I guess I'll draw it out. 36 minus 38
divided by 2.
2. Okay. Yeah, so now we get negative 2 over 2, which gives us a standard deviation of, I guess, negative 1.
Okay. For the z-score of negative 1?
Yeah, the z-score is negative 1. And then we just look that up on the table, and it tells us how many are less than negative 1, which will say this is how many.
16%?
Yeah, it'll be, about. I should look it up on the table. I have one here somewhere. I think that's why I try to make the point over and over in class that the problem is the exact same problem, whether or not you're solving for groups or the likelihood of group averages or the likelihood of individual observations. The only difference is what we calculate to be the spread changes, but everything else ends up being the same. Like, right, we stop talking about x's, we talk about x bars, but that doesn't change the actual math or the calculating. The centers literally ends up being the same number. So we, that's exactly the same. And then this just switches to using standard error of the mean.
Okay.
And so if you look up negative 1 on this table, it is 0.1587.
So it's like 16%.
Yeah, so 16% of the salespeople on average will have laptops that don't last more than 36 months. So 16% of the average groupings of 9 will end up this to the left of it, which based on the other one we solved, what was it before? It was, what was the number for the last one? We were just talking about raw scores.
30, wait.
Yeah, so it was negative 0.33. So I'm going to just look that up. So negative point.
I think the answer was like 37%.
Yeah, 37. So we went from 37% down to what, 13%?
16?
Was it 16? Oh yeah, 15.8. There we go. Yeah, so about 37 to down to about 16. So just as we noted before, like just these extreme tail results become less and less likely as you take bigger groups, because a group of 9 is very, very rarely going to be 9 observations all out here to give you an average this low, or all up here to give you averages this high. The averages will tend to be much closer to the center, which is why one standard deviation now is only 2 units up instead of being 6 units up.
Okay. Thank you.
Yeah, that's the entire problem.
Yes.
Cool.
Can I ask another question?
Yeah, sure. I mean, I've got an hour. You seem to be taking good advantage of it.
I know I was like here the other day too.
I know
I was the only one again.
For 40 minutes, and then one person shows up and goes, "How many people were here?" And I'm like, "Just you." But then I look later, and I mean, the videos have been viewed like 40, 50 times. So I assume somebody's watching them eventually.
Okay.
Yeah,
I'm
I'd say
just
these two
typing it out
problems
again.
here are about the hardest thing you're probably going to need for the first exam. Like, this is sort of the application of everything, right? It's understanding mean, understanding central tendency, knowing what standard deviation or variance are, understanding how that translates into standard error of the mean, how that affects the shape of the sampling distribution relative to the score distribution. Like, all of that is embedded in basically this problem.
Okay. I have another question. I'm typing one right now, but I have like one like that's just like I can say.
Sure.
So for the central limit theorem, does it measure center, width, and mean, or center, width, and height?
So the central limit theorem is not so much about measuring something. What it is, it's saying, so right, we always draw these little things. We draw like normals for you. Every time we say, okay, we're going to talk about a distribution, we give you a center and a spread. And we say, well, it looks like this, right? There's a thing and it goes up and it peaks in the center. But this is not always the case when we're talking about scores. Like, you can imagine something like, let's say there's I'm trying to think of a really popular song, and we're sampling people like, how much do you know of this song? There'll be some people who know nothing, right? A whole bunch of people who actually it'll look more like this, right? A whole bunch of people who don't know anything about the song, and then sort of middle amount of people, and then a whole lot of people who know a bunch. So this is not normal at all, right? Like, this is technically our arithmetic center, but the data is all over the place. And so because we don't have the normal shape we like to work with, we can't describe this easily saying, well, here's the center and this is the spread value, and now we know where the scores are going to be. Because by our old logic, if this is the standard deviation, we'd say, well, we expect 70% of the scores to be, in this range, plus or minus 1 standard deviation. But that is clearly not true here. So what central limit theorem talks about, it says, well, even if your data looks like this, if you have data like this and you take a sample that is sufficiently large, I think the book will either say 25 or 30. Usually they'll tell you one of those two ends. So rely on whatever the book says usually, but there's kind of just, in this range is where people generally draw the line of how effective this technique is. But what it's saying is, even if your data looks like this, if you take group sizes that are large enough, so something like 25 or 30, and then you take averages of each of those groups. So I pull out 25 people at random from this weird sample, right? I'm going to get a lot of observation down here, some here, and a whole bunch over here because that's where most of the people are. Maybe 1 or 2 here. And then I average all these and start plotting where those averages fall. Those will actually follow a normal distribution. So that will be the true center. And all that means is it doesn't matter what the underlying data look like. Like, even though there are some people who are really high and a lot of people who are really low and not many in the middle, if we just sample at random from this population of people and then plot the averages of our samples, so 25 people, we average their scores and plot those average scores will still follow a normal distribution, which is nice for us because all the z-score stuff we're doing relies on the normal distribution. We are assuming that we have data that is normally distributed. And that might not be true at the population level as far as individual human beings. Like, these are people who know a lot, these are people who know nothing. But if we sample from everybody and then take an average of the people we've sampled, and plot where those averages are, they look normal. And you can see this like it makes a lot more sense in things like coin flips, which are very strange, right? We understand you either flip a heads or a tail, right? Every coin flip is a head or a tail. So if we just plot this as some frequency distribution, we'd say, and we'll call, tails 0 and heads 1. We have a distribution that looks like this. We have a whole bunch here, nothing in the middle, and then a whole bunch here at 1. So even if this is the case, if I flip a coin 25 times and say, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So at random, I flip it a bunch of times. I'm going to get roughly an even amount of heads and tails. And then if I average out the zeros and ones, I will get a mean that's somewhere around 0.5, right? So no individual coin flip is ever half heads and half tails. But if I average across all my groups of coin flips and then plot where those average values are, they will center at 0.5. And sometimes I'll get a little bit more. I think I called this heads. Just keep it straight for myself. So sometimes I'm going to get a little bit more heads than I get tails. But with an even amount or with an even frequency, I'm going to get a little bit more tails than I got heads. So the sampling distribution of coin flips is normal, even though it is impossible to imagine coin flips being normally distributed as individual observations, right? You're only ever going to flip a heads or a tails. But if I sum across a big group of heads and tails flips and average out, on average, what did you get? I get a thing that looks normally distributed. So that is kind of how that's what the central limit theorem is trying to describe. It's trying to say we can avoid the fact that our data are not usually normally distributed, or many times they're not, or we just don't know if they are. So no matter what the underlying shape is of the frequency of individual observations, that if you sample large enough groups, usually about 25 or 30, and then average across each of those samples and plot all those averages, that those averages will follow a normal distribution. So this is our X bar score, right? So this is a little bit more heads. This here is a little bit more tails. This is an even amount of heads and tails. And you can see it becomes increasingly unlikely. Like these are mostly heads flips. These are mostly tails flips. Those don't happen all that often. More than likely, we're going to get some value in the middle because it's an even mix of heads and tails because it's random. And this is all the central limit theorem is trying to say. It's trying to say, even if our data looks like junk, our averages will look like that. And it's just describing where the group averages are going to fall. It's not talking about any individual observation. It's just saying, in theory, if you could infinitely keep taking samples of size 25 and then plot wherever those things are, they would have a frequency distribution that looks like this, which is that in the center, most of the group means will be near the center. A few will be very low, a few will be very high, but on average, they'll look like this and follow a normal distribution, which means we can use the Z-score to describe them and just figure out things about like, so you can imagine this is Vegas and I'm trying to, so this is kind of going a little bit beyond what we're doing. This is like next week's stuff basically in class. But in Vegas, you could say you have someone who's flipping coins, you're betting money on it, and you want to know if it's a fair coin. If you flip the coin 100 times and you get a value like this, the average value is 0.8, which means 80% of the flips were heads. You would immediately be suspect that this is a fair coin. And that's the kind of thing you can do with a sampling distribution. You can say, well, I'll flip the same coin 100 times, and now I want to know, does the average this coin give me make sense with it being a fair coin? Because if it's a fair coin, it'll look like this. It'll be about evenly heads or tails. We know sometimes this stuff will happen, but it's very unlikely. So if I do a sample of 100 and get something like this, I'd say, well, that looks suspect. Let me flip it another 100 times and see what I get. And if I keep flipping this coin, infinitely 100 times, and this one coin follows a distribution that looks like that, I can say this is a biased coin. This coin is weighted in some way that's going to make it land on heads more than it should. It's not a fair coin. And so this is kind of where we're heading in the class. Like the reason we're learning about central limit theorem, right now we're just talking about mostly describing the data we have, right? Like about laptop failures, like how many of these laptops are going to fail, or how many of the salespeople's average laptop failure rate is under this many months. But next in class, we're going to talk about, okay, we know some stuff about the population. Now you take a sample from that population and give them a pill that's supposed to like make them less depressed. Do they look different than the regular depressed population? Does the average that's coming out of your group seem very unlikely relative to the population's average?
Okay.
So that's kind of the next step in the class, is taking that next jump of, once you understand how we're able to turn individual observations to describing where average observations fall or where the group means fall, then we can start comparing group means to the population and say, does this group mean seem like it's coming from this population? And if it doesn't, we can say, well, this seems like an unfair coin. Or, you know, similarly, if it goes on the other side, we could say, well, this coin is biased towards tails. It's very, very likely that you're going to get tails with this coin. So whoever using it is tricking people to say, I'll bet you, you know, $10 it's heads or tails. If I know I'm flipping this coin, I would bet heads every time because I would win 80% of the time. Where most people assume you're working with a fair coin that they have an even shot of winning. But if I know the coin is unfair, then I am basically have more information than you do, and I'm able to win more than you are.
Okay. Well, my question about the central, I was just asking because there was one of the questions and it said that it describes the center, width, and blank of the distribution of means. And is it, so it is mean, the center, width, and mean?
Yeah, although the center is the mean usually. Like that's what the central limit says. It says this is the center, because if I average all these, that's still the center of it. It's just that the sampling distribution will follow like this around the center.
I mean, well, the options are like mean, range, shape, height, or variance. That's why I was just confused about which one it was.
Okay, so what is the exact text of it? Oh, I see you say, did my question come through?
Yeah, I asked another, I just typed out the other one because this one was just, I could ask like,
oh, I
can't, it didn't have any numbers, but okay, the other one had, it was about, it had like number 5 and it was about something with kids and math test.
Okay, I see. In the population of children in grades 5 in the United States, 25% score below 5 on a math test. Marjorie obtains a random sample of 102 grade 5 kids. What is the probability that the mean of this sample will be below 5? Yeah, so this is really similar to the last problem, but we can do it again here. But I think the concept
I just saw like a lot of these, and I didn't understand. I just want to understand the concept of it because there was a lot of them, and it was always like less, and I didn't really know. Is it just because it's? I don't know actually.
So what do you mean it's less? I guess it's to clarify that part.
I guess the answer is less than 25, but I don't know why. I just kind of. Yeah, I just want to know why.
Options. Okay, so in the population of children in grade 5. So here we're talking about the population of children. So just like I always do this for myself, like, okay, these are scores. So I just write X, where the sampling are at X bar to just remind myself what I've written down from the problem. Because it's very easy to quickly like translate word problems onto your page and miss steps or, you know, write the wrong information somewhere. So based on this, okay, we're saying grade 5 kids, 25% score below 5.0 on a math test. Marjorie obtains a random sample of 102 kids. What is the probability that the mean of this sample will be less than 5.0? And what are the options there?
100, 25, less than 25, more than 25, but less than 100.
Okay.
And the answer, I guess, is less than 25, but I just want to know why that's the answer, like how you would go about figuring that out.
Yeah, so we know, yeah, you're correct that it is less than 25. So again, just drawing these, the first thing we want to say is we're interested in the score. It says the score of 5.0 corresponds to about 25% of the people, or 25% do worse than 5.0. So we immediately know 5.0 is less than this, right? It has to, because if it's this high, then half the kids are doing worse than that. So we have to move left. So it's somewhere over here, the score of 5.0. And then whatever's left over, you know, this little bit here, that ends up being 0.25% or 25%, or 0.25 of the whole of 1. So, okay, so that's all we really know here. And then they're saying that we take a sample. Oops, wrong marker.
Well, how do you know that it's less than the average for 5 again?
So the reason we know it's less than average is that, okay, so what if I just told you mu? How many scores are less than mu?
Half of them.
Yeah, so this whole entire side is equal to 0.5. So if I tell you that 5.0 corresponds to 25% less, that score can't be on this side because then the number would be greater than 0.5. So that's all I'm working with, right? So if we understand, like, if I come out to here, the probability is basically 1 or, around 1 because we pretty much captured all the distribution. It ends up being somewhere less than this value. And we move over here, we know this is 0.5. Around here, that's some halfway point, 0.75. But the idea is that the numbers are going down. So we just know that it has to be to the left of mu because it's saying there's only 25% there. But I mean, does that make sense? Or because that is it's not an obvious thing. Like, it's nothing we've ever told you. It's a thing if you just kind of work with these problems enough, you get a sense for like, oh, okay, here's the kind of information I can extract from what they've told me. Because this is a much harder case because they didn't give you mu. They didn't give you sigma.
Okay.
But if you understand how this, like, if you understand the properties of this distribution, you can start making educated guesses into where things are likely to appear. So if I tell you a score of 10 corresponds to being better than about 80% of the population, immediately, like, where can you tell me this thing's going to fall in the distribution? Is it to the left or to the right? So I say X is 10, and that is, 10 is greater than about 80% of the people. Then a score of 10, where would it fall in this distribution? Is it on the left side or the right side?
The right side.
Yeah. So that's kind of the whenever you get less information, you want to think like, well, what can I figure out based on what they're telling me? And in this case, you can't really figure out much. We're just figuring out that essentially they're saying 5.0 to the left of it is some tail amount of values.
Okay.
We don't generally know how far away it is. We just know it's to the left somewhere. But what we do know is that when we make a sampling distribution, so if n is 102, here the standard deviation is sigma. If we're talking about the sampling distribution, what's the center of it? So these are all X bar scores, right? Like, essentially we're pretending we can take infinity X bar scores. So based on what we know, what could you tell me about this distribution? What is its spread? And the answer is not a number. So if you think like symbolically, what is its spread?
100%? I have no idea. I don't know what that.
Okay, so up here, what is the spread of this distribution? What do we use to describe the spread of the scores?
I don't know.
Okay, so if we think about a normal distribution, what things describe a normal distribution? Like, what properties do we usually want to know to be able to solve problems?
Just like the properties, it's like asymptotic. It's asymptotic, right? Asymptotic is not the word, and then I don't know the wording that you're asking me. That's why I'm not going to be able to answer.
Okay, so what I'm trying to say is that to solve any of these problems, right? We needed mu, we needed sigma, and usually we need some X score that they want us to figure out. So these are just properties of this distribution. This is its center. This is the spread of the distribution.
Okay, so spread is just the standard deviation.
Yeah, it's just some number to quantify like how spread apart is it. Like, if this number is huge, it'll look real flat. If it's real small, it looks tall and pointy. So the spread here is sigma, but what is the spread down here?
It's sigma divided by the square root of the population.
Yeah. Right. What do we call that?
Standard error of the mean.
Yeah. So the standard error of the mean is sigma divided by the square root of that. 102 is pretty big. We can assume if we take the root of it, it's something around 10. Right. Yeah. 10 times 10 is 100. So we can just say, well, this is about a tenth the spread of that distribution.
Okay.
And if we just know the way spread affects these things, we know that if the spread value gets bigger, it looks more like this. As the spread value gets smaller,
It's going
it
to get
looks
narrower.
more like that. So based on
Okay.
the fact that this, score 5.0 encompassed 25%, if we took that same score and put it down here, we can just see that there's less tail here. So this, whatever this small proportion is, above 0, it's clearly smaller than 25%. And it's because these are basically the same distributions. What's happened is we've just changed the spread value. That's all that's happened. We've taken this and said, make it more tall, I guess.
So
Right?
just
We've taken
because
this
you've
shape and
made
said,
it,
do this.
just because the standard deviation has become smaller, then like the percentage becomes smaller.
So what it is that as the spread gets smaller, that means the scores end up more concentrated in the center, right? Because if I take an average of 100 people, I'm never going to get 100 observations all out here. So I'll never get an average this big. So these what we call these extreme values, that just means they're moving away from the 0. So either extremely big or extremely small. Extreme values become less likely as the standard error or the spread of the distribution gets smaller. So that's what this purple thing is here. That's a really small standard error, which means that from mean to mean, they're going to be very close to the true value of mu. So these values that are unlikely over here, only 25% are ever going to be this low. Our averages are going to be even are even more unlikely than our individual observations, because it's unlikely if I take 100 people that they're going to end up averaging, in this range. It's much more likely that if I take 100 people, they're going to average somewhere in the center, because they're coming from this distribution where most of the scores are in the middle. So if I'm pulling at random, I'm going to mostly get middle scores. I'll get a few low, but I'll also get a few high, and they'll kind of cancel each other out to give me more values that look like the middle when I average them. I think that's all it's saying. If you can get so literally this distribution has this shape, and as we just take bigger and bigger samples, it just starts to suck in like this, right? So I'm just drawing half of it, and it ends up looking like something like this. Like if you have 1,000 people, it just looks like a line almost. It looks like everything is right here.
In what way could, if you had so basically whenever there's a sample of the population, it's always going to make the percentage less than.
It makes these extreme percentages less, but it'll make the small interval, plus or minus 1 point around the center, will become more likely as the standard error gets small, right? Because all the scores start looking like the center.
Yeah.
So the center values become more likely, and the tail values become less likely. So it's literally just like a sucking up. Like if you sort of just pressing in the sides, and it just starts pulling upwards like that.
Okay.
But yeah, it is a little tricky because you do have to make some inferences, especially when you can't rely on, well, if you know the formulas, right, you could just do the math of it. But sometimes they like to give you things where you just are not able to do the math, and you have to purely try to conceptually understand, well, even if I don't know anything, I could say, well, this is mu, and that's sigma. What would happen if I take a sample of 102? And you're like, okay, well, sigma, we're going to calculate standard error, and that's going to make it smaller because we're dividing by square root of n. And then what does make it smaller mean? Which means make it look more like this. And then how would that affect these probabilities? It's like, oh, these become less likely because all the scores the average scores don't end up here that much. They end up much more likely to be here. So of all the averages I'm going to produce, there's going to be very few out here and a lot in the middle.
Okay.
But I mean, does that make sense? Because I really want to. That's my main point.
I think so. I just like to see it visually. I just like to work out problems with some numbers, or just to see it so that it's not just I just want to see how it works so that I can apply it to ask another another question on the exam.
I mean, I think so. Lots of times to just kind of prove it to yourself. This is generally also how I ended up learning this stuff. It just anytime we give you a question that says, "Here's a mu," it's 100. How you like to easy math. Here's a sigma of 10, and that lets us know, okay, well, we've got a distribution. There's 100. 110 ends up being one standard deviation up. And now you can just start picking probabilities and say, okay, a score of 113, how many are going to be greater than that score? That'll be some number, X, right? And then you can say, well, now if I took the same data, but I took a sample size 16, how's that going to affect things? So this distribution now still centers at 100, but now instead of being up by 10, it's 10 divided by, 10 divided by square root of 16. It's really 10 divided by 4. What's that? 2 point something. So the point is that this is, 102. And then you can look up that same score of 113, which is going to, be right here, and say, what's this probability? And that number will almost always be less than X. So even if the problem only gives you these two things, you could always just ask yourself, well, what if I took a sample of 16? And then you can solve for 16 and then say, well, what if I took a sample of 200 and see how that affects the value? And it'll be basically X is going to be, so if we call this purple area X, X is going to be greater than the X of when you take a sample of 16, and that's going to be greater than the X of a sample of 200. So every time the sample's getting bigger, the distribution's looking more and more sucked in, which means these tail values are becoming less and less likely. So we're using the same cutoff of 113 as far as like how many scores are above it, and you can just watch how the sample size affects the probability of getting values out here, which will become very important in the next part of class, because the next part of class we're going to start talking about like actually running experiments and like the real meat of what psychology is. And like, if you're a clinician and you want to try a new therapy to see if you make people less depressed than the current therapy, how do you assess its effectiveness? And this is really how you're doing it. You're saying, well, we know things about the population, and based on that, we took our people, we gave them some intervention, and they gave us an average depression score out here. And now the question becomes, well, how unlikely is this average score? Right? Because if the population's 100 and your depression group that's supposed to be getting better gives you an average score of 99, are you very convinced that you had an impact on their depression? Or is it more likely that randomness sometimes will just give you 99? So that's kind of where we're trying to head in class. It's that once you get this stuff, you can start understanding how you design studies and how we actually like assess the effectiveness of the things we're trying to do in psychology, or the things we're trying to figure out. Like, you want to know how people's visual perception works, and you want to test two competing theories. Well, you need statistics to help you figure out whether or not you've affected their visual perception. Like if you think visual perception needs color to work, then if I give you a display with less color than usual, you should be doing worse. And when I take a group of people and do that to them, how do I know if they've actually changed? And the way we figure that out is saying, well, look at the group's average, compare it to the population. Does it look different than the population? Is it different enough to convince us that we've had an effect? Or is it different in such a small way that it's likely just random noise?
Okay. Did my other question come through on like the chat thing?
Okay, is it true if the parent population has a mean of 50 and a standard deviation of 10, then the distribution of means will have a mean that is equal to 50? I would say that's true. Well, does it say it's normally distributed?
I don't know. The question said it's either less than 50, more than 50, less than 10, more than 10, or none of the above. And I thought it was none of the above. So I thought it was that. Because isn't the mean always the same, even if it's like the mean of the the distribution of means compared to the parent population one? Isn't the mean always the same?
Yeah. So when we go from scores to sampling distributions, we get the same mean. So yeah, the correct answer would be it's the same. But if
it's equal to 50.
Yeah.
So it'd be none of the, yeah. I was just wondering because I wanted to make sure I understood the concept of it. It wasn't like, okay.
Yeah, you're correct. That value would be the same. I think a lot of this is made a little bit more confusing by the fact that we're kind of giving you cases that don't really exist in the real world. Like, it makes it easier mathematically to get, but I think you guys are wrestling with the idea of like, what are we actually using this for? And the thing is that people don't really use this stuff. Like, this is sort of just a fundamental probability theory that allows us to do the next stuff, which is what we actually do, which is sort of the whole next section of the class is, okay, now we're working with real samples of patients. We don't really know the population values, and there's more uncertainty there. And how do we deal with that case? Because here is kind of the perfect case. Like, if I knew everything about the population, I can pull 16 people out, do something to them, and see if I've affected them. But in the real world, we don't even know these population values. So we end up estimating both these things and comparing it to the estimate, and it gets sloppier. But in theory, this is like the reason we're doing stuff like that.
Okay, and then I have one more question. Do we have to know how to transform a z-score to a standardized score? Because I feel like we've been more doing like transforming the raw score to the z-score. But
A standardized score, usually that's what we call z-scores, or we call them like standardized in that.
Yeah, but I don't know. I just saw like there was like in the reading from the book.
What did it say?
It said x equals mu plus z sigma.
Yeah, so here's what the book is doing, and this is what I advise everyone don't do. So this is the z-score formula as you know it, right? X minus mu over sigma.
Yeah.
So the book will teach you stupidly, it'll do this, right? So it's just doing the algebra for you. It's saying, okay, we can move the sigma over. This is divided by sigma, so we multiply both by sigma. Now we get z sigma is equal to x minus mu. Now we can add the mu to both sides. Now we get z sigma is equal to, our z sigma
plus mu.
Yeah. Plus mu is equal to x. That's actually not a different formula I would bother remembering, as long as you can turn this thing into whatever you want with algebra. Like if you
I was just wondering if we need to like know how to do that, because I feel like more so it's just been applying the top formula that you wrote.
You might need to know how to do this. Like there could be cases where I could say, you know, you get.
What would the question be like if you needed to use the formula to find?
So the question that I could do it completely backwards on you. I could say, okay, we have a population. So actually, let's solve this right now, which is, this is probably about the hardest thing we could ask you to do, which I don't think we've asked you to do yet. So I could say, we've got some distribution. It doesn't really matter what we're measuring. The center is 100. Actually, can I do this? Okay, the standard deviation is 20. And I say, you got a score that was better than 30% of the population, right? So you are greater than 30% of the population. What score did you get?
I mean, couldn't you look at like the z table?
Yeah, so right, so if you look up the z table, it'll just, you can figure out what that number is, right?
Like you just have to find like, wait.
So what are you looking up on the z table?
You'd have to find the z score and then wait, never mind. I was gonna think you could match the percent to a z score, but I don't know. Maybe I'm wrong.
No, that's actually correct. You have it right.
Really?
We want to find the z score that corresponds to 30%.
So wouldn't you just kind of have to like look all over the z-score page and attempt to find it?
Yeah, although I mean the z-score, it's the way it's structured. You can just follow the first row down until you get to about 30. So like, right, I followed this first row and at negative 0.5.
Yeah, negative 0.5.
Yeah, so then z is equal to negative 0.5. Well, now we have everything we need, right, to solve this problem, because we know the formula for z.
What was like the question of the problem?
The question is, we want to know what score did you actually get on this measure? Like, I can tell you this is how well you placed relative to everyone else, but if I want to know your actual score, you can actually figure it out with this information.
Okay, so this is transforming a z-score into a raw score.
Yeah. And you can see it's the exact same thing, right? So we're just saying, this is the formula for z, and we just plug in the things that we already know. Or let's just say let's transform it so we can solve for x. So we can just move stuff around and say z times sigma is equal to x minus mu. So this is what we did before, right? Z sigma plus mu is equal to x. And these are all known numbers, right? We figured out the z is negative 0.5. I told you sigma already is 20. I'm going to add to that. We're going to add, what was mu, 100. Oops. And that's our x score.
And
so this
like
is just taking
like that technically the person got on the exam.
Yeah, so this would be the score that you get to land you better than 30% of the people.
Okay.
But you can see in theory, all you need to know is, as long as you can remember this formula and just apply some pretty basic algebra, you're solid. Because I wouldn't try to commit these to memory.
We know that because we haven't done as many like problems like that as I feel like transforming, just like using the first equation you wrote on the left.
Yeah, usually they'll throw one at you on an exam, because this is kind of the professors want to see, like, could you figure this out? Like, we didn't tell you
All
exactly
right.
how to do this, but if you get the general principle that this is pretty flexible, and if we know 3 of these 4 values, we can always solve for the 4th. And as
Okay,
long as
so
you
then
have
it's
like
good that
some
I
decent
asked.
algebra, yeah, you can get it.
Okay, thank you very
But
much.
yeah, don't try to commit these to memory because you will screw this up. You'll get to the test and you'll forget if it's minus mu or plus mu. It's so much easier to remember this one thing and then just move it around as you need it, because
Okay,
that's what the class gets harder, is that people try to memorize every special case, and I tell them you're much better off just keeping the general case and then learning how to work with it. Less
okay,
stuff to keep straight, less stuff to confuse.
okay. Thank you.
Cool. Take care.
You too.
Look like there are no other visitors. I'm in the last minute. Just want to tell everyone good luck in the exam tomorrow. And we'll see you all bright and early. You don't need to bring Scantrons. In the third video, I explained how to use the z-tables. I know we had a lot of questions about it, so you can see that again. But otherwise, good luck. Talk to you all tomorrow.